All right, so we're trying to make the largest box, as we said before lunch. Probably has something to do with derivatives, as those help us to get maximums. But let's do a quick show and tell. Now, this is not meant to embarrass anybody. It's actually just to help you guys see some of the different choices. The class is small, so I need to give some input. Sometimes a student would have done this. There's the cookie tray box, kind of fitting that we just got past cookie season. But you kind of think, geez, it's got such a huge surface. But the problem is that the height, if you will, is too small. I only cut a 1/4 inch off of this, so I get to multiply by 1/4. Well, you know what happens when you multiply something by 1/4? It actually gets smaller. So the volume of this cookie sheet is only 21. Okay, again, it might be good for cookies. What's your favorite type? But not going to give us the largest volume. Okay, again, that one was 21. You're looking at yours and you're like, mine's better than that. Now, if you cut, just kind of cut the edges. It looks like you cut like about 2 inches, maybe a little more than 2 inches. You can get 47. So that's double of my cookie sheet. This thing's 47. It's also got some other things going on. But you can get 47. And then we can, I should have did this one first. I mean, it looks like a nice box. You could put like pine cones in it, maybe put a candle in there. Now, it's a nice looking box, but I'm going to trust your math. It only comes out to be 45. So, I mean, it seems decent. It's got a nice big side to it here. What cut did you do? 2 3/4. So it's bigger than Reagan's. So, but that gives you 45. It's a similar looking box, isn't it? It's a similar looking box, but I'm going to trust your math. It's 57, almost 58. What was your cut?
2.5, a little less.
2.5. So we're sort of dancing around like 2, 2.5, 2.7. And again, our numbers are similar, but geez, one was in the 40s, now we're in the 50s. And here's a volume of 60. Here's a volume of 60. Your cut was 2 exact. So we're actually making the cut smaller, but the volume keeps getting bigger. Okay, now again, we're looking for the biggest volume. There's some other options. Is this 65? 63. Okay, no worries. It's also a size of 2 until we get to this box. Now, I'm going to give you guys both credit for this because your math is right, but there's something different about your cuts. Both of these students here got cuts of about 1.5, right? And when you cut 1.5, if you can't read in there, it's 66, which is actually the largest volume so far. And in fact, it ends up being the largest volume. It's like the best you can get. Now, again, they should be the same size, but your math is right. Again, 1.5 will give you a length times width times height. That's 66. A lot of the boxes look the same, and yet it's only a difference of 1/2 inch, and you end up with more volume. By the way, I forgot to reveal this one, but this is sort of like the takeout box, like put some General Tso's in there. But this one only ends up being 37. Okay, it's kind of like there's too much cut. There's too much cut, so the one dimension gets too small. So how about the math? And this probably will be the point that you want to start to jot some things down. But connect this to the box problem, okay? Because we're still doing the box problem. Again, we know that the best answer is 66, but let's discover that answer with some calculus. It was neat to see you guys do some thinking ahead of time instead of just doing a random cut. I don't think I saw this, but yell if you did, because I want to give you credit that sometimes there's a student that will use an equation. Okay, it's all right if you didn't, but again, if I missed something, let me know, because this is kind of like the algebra way, which you'll eventually use calculus. Now, the algebra way is to realize, like you guys did with numbers, that the cut that's made here is really what's unknown. How big do I want to make that cut? The cool thing about that x is that it also ends up giving us one of our dimensions, and it can be used to describe the rest of the dimensions, okay? Because this length, if we want to call it the length, is guaranteed to be, as you guys were calculating with your numbers, it's guaranteed to be 11 inches minus your 2x's. Again, it was neat to see you guys do that with numbers, but we can actually write that as an equation. We can do the same thing over here, where we think about this dimension. I guess we'll call it the width, which is also guaranteed to be 8.5 minus these 2x's. And really, just like that, we have a length, a width, and a height, which I know you guys realize is unknown, but I can still take those expressions for the length, for the width, and the height. So I can take 11 minus 2x, I can take 8.5 minus 2x, and then multiply that by x being the last dimension, and we have ourselves a volume formula. Now that's exactly what I'm doing. I'm making a formula. I'm going to trust that you guys could do that algebra. Make sure you realize that it's probably like the FOIL method. You also have to distribute x. And I'm not honestly going to skip some of that combining like terms and just get ourselves all the way down to 93.5x minus 39x squared plus 4x cubed. It's all right if you're just copying those numbers down. Make sure you're doing a little bit of thinking. Just maybe like the easiest thing to think about, if you do the last part of the FOIL method, that's of course going to give you 4x squared times x is why I get positive 4x cubed. Similar for the rest of these terms. They would come from good basic algebra. Now, yes, that's a volume formula, but yes, I want to find its maximum. I guess what I really want to do is I want to analyze this cubic. And we know that cubics go up and down and then back up, but I want to analyze this cubic to find where that up and down part is. Basically, to find its critical points. So that's calculus code for a derivative. Okay, we're still in the derivative chapter, and the derivative of this cubic, not too hard to do, just change those exponents and all that good stuff. So we get 93.5 minus 78x plus 12x squared. Now, you guys, we'll do some problems like this. As you can see, the numbers are starting to get a little bit more like an application number, a little bit less of just a typical book problem. But I still want to set this thing equal to 0, because of course, when you set it equal to 0, you're finding those critical points, which, by the way, are going to end up on a number line. We're headed towards a number line, if you're wondering. Now, if you're looking at this saying, yeah, how am I going to solve that? Well, it is a quadratic. Quadratics sometimes can be solved with factoring. It turns out that the numbers aren't suitable for factoring because, again, it's not really just a textbook problem. But there is another way. It's something you would have done even since Algebra 1. It's called the quadratic formula. Okay, let's set up the quadratic formula. If you've had me before, you know that I say that you want to be able to teach the quadratic formula to your kids, so you still remember it, right? Because you have to be able to teach it to your kids It's the opposite of b, so it's the opposite of negative 78. Is it coming back to you? Plus or minus the square root. Okay, so we get a b squared minus a 4ac. Please be careful, the letter A is actually a 12. The C value is actually the 93.5. Okay, and all over 2A. All over 2A. Now, as I said, you guys will actually do some problems like this. Like, it's not going to be that far out there to have to use the quadratic formula. Let's kind of shortchange this a little bit and keep on rolling, because a lot of this you would do on a calculator, so that you can see at least one more step. The square root value comes out really close to 40. It's actually not exactly 40, but to make it simple, I'm going to simplify it to plus or minus 40. So I got 78 plus 40, 78 minus 40, and you probably won't be surprised to see that this comes out to be two numbers. Okay, it comes out to be 1.5 and 4.9. Actually, to two decimal places, 1.58 and 4.92. Now, here's the part of the problem where I want you to make a connection. We build a box, not just to waste time, but we build a box so you guys would understand that the cut is x. And you've seen a few of your classmates say that the best cut was the one that was 1.5. It actually turns out that it's technically a little more than 1.5. Okay, but that's your x, that's your cut. What about this cut right here? 492. Okay, well, let's go to the number line. Maybe pretend that you don't know what these numbers are, which is how you're going to approach most of the problems. You don't know what the answer is. But if you put those critical points on a number line, you can figure out which one of them is the max and min. Now remember, to do this, you're plugging in to the derivative. The derivative is still this nice 93.5 equation. I just need to plug in some numbers that are in every interval here. Okay, so I could plug in 0. That would mean that I'm not making any cut, but technically, by theory, 0 is in that space. I guess I could plug in 3, and I could plug in 5. I just want you to understand that you can do the same thing, and you'll have to, so that you can figure out if the derivative is positive or negative. It's pretty easy to plug in 0. I always like to pick that one. It's just going to give you 93.5 minus 0 plus 0. So it's going to give you 93.5, which is positive. If I plug in 3, it's going to come out negative. And if I plug in 5, it's going to come out positive. I'm talking about the value of the derivative. Even though this is an application problem, we still have a familiar graph that goes up. And then the negative says that it's going to go down. And then the positive says that it's going to go back up. I really would like you to make this connection with me that the graph we just drew is actually the volume graph. Please understand that this volume equation is a cubic. It's exactly what we have right here. And so the maximum of this volume equation is obviously and clearly this number, which again, as some of your classmates showed, is actually the true maximum. Now, you should find the volume. So this is just the maximum cut, but we should go back and find the maximum volume. So it's kind of one of those things where we say that you're going to cut 158, but the volume that goes with 158, well, just like you guys did with numbers, it's just taking 11 minus 2 of those cuts, taking 8.5 minus 2 of those cuts, and then multiplying it by another 1.5. So basically plugging 1.58 into our equation. And that ends up giving you these 3 dimensions. It's going to be 7 by 5 by 1.5. Okay, I plug into each of these 3 spots. I get 7 by 5 by 8 by 1.5, which actually is a little more than 66. But we still say congratulations to the students that got that. You guys are going to find out that much of this lesson is about creating formulas. It's going to feel a little bit more like algebra. The calculus is the easy part, if I can say that, because it's just derivatives. But ultimately, it was this equation that we created that allowed us to do this calculus. And that's going to be what you guys spend kind of most of your time sort of fooling around with and trying to figure out. I want to do another one with you before this period's over, but let me kind of help you see that we're just taking the idea of maximums and minimums and applying it to what we call optimization. Optimization is really just a maximum or minimum. But I want you to hear that language. If you want to jot it down, you can. But it kind of makes sense, right? An optimal value is a maximum or minimum. And just like we learned in the last section, or maybe in the last half of the chapter, that's always going to be when the derivative is equal to 0. Okay, remember, if a derivative is equal to 0, you're going to be at a maximum or minimum. So what else? Like, what else will these problems look like? What are we going to have to be able to do? Many of the problems fit into a little method. And the method is to come up with what we call a primary and secondary equation. I'll explain that we kind of did that for the box problem, but it's going to be helpful for you guys to hear this and to use this strategy. Again, a primary and secondary equation. What's the primary equation? It's basically the quantity that you want to optimize. Okay, I think it is true that it's the most important equation. So I would call it the primary. It's the one you're trying to optimize. But the secondary equation, it's also important. I don't want to be spinning this like it's extra information. It's actually important information that you're going to end up substituting. You'll find out that you end up substituting it into the primary equation. Maybe I should have wrote that down, but you'll catch on to that idea. For the box problem, even though we've kind of already done it now two times, the primary equation was the volume equation, quite simply because that's what we were trying to optimize. From the get-go, we wanted the biggest volume. And again, that's usually kind of obvious. The secondary equation actually was the sketch. Okay, the sketch that kind of allowed us to create these expressions for the length, width, and height was secondary. Okay, now, a lot of you, this is just going to kind of be natural and common sense, but I still want you to hear the language of primary, secondary, and I'm going to show you in a new problem why it makes it easy. Let's do one more problem. I always like to show you 2 on the first day. It is kind of a word problem, so maybe you have to jot some stuff down. We're trying to get the smallest perimeter of a rectangle with an area of 36. Now, to try to follow this primary-secondary sort of method, you just really have to read the problem and ask yourself, what are you trying to optimize? What are you trying to get the maximum or minimum for? Okay, I hope that it kind of stands out to you that it's the perimeter, but you want to realize that it's a word. And when we get into some harder problems, something you can do to make your life a little easier is just first recognize that the primary equation, it's a word. In this case, it's the perimeter. Now, it quickly turns into a formula. Okay, now here's kind of the part of the lesson where you have to think about the math that you've learned. I'm not trying to quiz you on geometry and such, but you should know that the perimeter of a rectangle is always two x's plus two y's, or two w's plus two l's. So we have a nice little perimeter formula. Don't panic if you can't remember a formula. It is something we can look up, etc. The primary equation. Now, there should be something about this equation that kind of catches your attention. Although it's the first time you've seen this, it's got two variables. We're not going to be able to do the derivative with two variables. Okay, not yet anyway. At the end of the chapter, we'll learn how to do that for a different problem. That's why we have a secondary equation. The secondary equation takes the other information and helps us to do a substitution. Now, the only other thing that's written up there is the area. So there's really not much to think about, except to realize that the area equaling 36 is also a formula. And so again, we have to think about the formula of a rectangle. It's not supposed to be too hard, but you would have to say that 36 is equal to xy, length times width. Okay, now the nice thing about the secondary equation is that it gives us a connection between x and y. And that connection is that when they multiply, they equal 36. Or if I choose to solve it for y, the connection can also be that when I divide by x, that equals y. And so we're getting ready to do a little substitution. We're getting ready to take our perimeter equation and have it be just one variable. And so, of course, y equals 36 over x gets substituted. And you'll come to realize that now we have a formula that we can derive. I would simplify it. Yes, I would simplify this. 2x plus 72 over x. That's probably as far as you need to simplify it. You could get a common denominator, and I'll kind of leave that up to you. Okay, make sure you get this. I do see that students forget to do this on a test, and that is that before you set it equal to 0, you have to do the derivative. Okay, we've done it so much, but don't forget. So we're going to optimize. And to optimize is really just to do the derivative. It doesn't have to be f of x anymore. It can be p of x, so p prime. You should put the prime symbol so you know that you've done the derivative. Now, the derivative of 2x is just 2. The derivative of 72 over x, that's actually always worth discussing. Are you catching my drift here? This is something that we want to take away someday. But to do the derivative of 72 over x is to think negative exponents. And of course, to think about them carefully. so that when you subtract from that exponent, you actually get more negative. You get x to the negative 2, which I'm going to flip back down to be over x squared. All right, it's not just kind of like your nice little derivative, but it still can be set equal to 0. And you're kind of thinking about what you've learned about solving equations. You know, an equation like this, there's different ways to arrange it. I could move the fraction over to the other side. Eventually, you're going to do some rearranging and arrive at x squared equals 36. I hope that you basically divide by 2 and get a little rearranging so that we can actually solve for x equals plus or minus 6. Now remember, x equals plus or minus 6 represents the critical points, but it also represents the dimension of our rectangle. It represents the x dimension. And it sort of brings up a point here where one of these dimensions just doesn't make sense. You're not going to have a negative dimension. You're not going to have a negative dimension. So I really don't even need to put it on my number line. But what I should check is that the graph actually is going to be a minimum. And if I plug in a number to the left of 6 and to the right of 6, I will quickly discover that I do have a minimum. I have a graph that goes down and then back up. Thank goodness, because 6 is the only number available. So that means that 6, well, it would have to be the minimum, unless, of course, we made a mistake. Now, the question for this problem is actually, what is the perimeter? So we have to make sure we answer the question. If I just stop and circle 6, I'm not quite done. What I really should do is I should go back and figure out what perimeter goes with the number 6. Now, you realize that you can do this many different ways. You can plug 6 back into your area equation, and you can find that y equals 6 also. So we end up with basically a 6 by 6. And if I have a 6 by 6 rectangle, well, that's going to come out to be a perimeter of 24. I could also just do it the old-fashioned way, and I could plug 6 back into my equation for x and y. And that easily shows you also that you get 24. But I'm just saying that once you have your answer, you can kind of decide how you want to come up with the final answer. And we'll show you some more tomorrow. Okay? You can take your box along if you want. A lot of times we do that lesson before Christmas. So it might serve as a little gift that you could give someone.